I worked through sample problem 1813 first because I like doing that so you understand why this solution has the pH that it does. So we're going to kind of treat this as though you've looked at sample problem 1813 first and kind of predicted what the pH of the solution is, acidic, basic, or neutral, and then we'll do the quantitative aspect of that in thinking about what the pH of the solution actually will be. So kind of springboarding off of problem 1813, they tell us that we have a sodium acetate solution and we'd like to figure out what the pH of it is. So they tell us that we're going to abbreviate sodium acetate NaAC. So we've got all sodium salts being soluble, so in the presence of water we're going to make sodium ions and acetate ions. As we saw in our previous problem, there's going to be no contribution to pH from sodium ions. They're a small but not highly charged metal. Acetate has the potential to contribute to pH if it comes from if it is the conjugate base of a weak acid. Well, acetic acid is a weak acid. Here's the chemical structure of acetic acid. Here's the chemical structure of acetate. Having that carboxylic acid functional group means that this is a weak acid. And just like we did in our last problem, we need to think about the chemistry that this acetate ion can undergo when it's in solution. So acetate ions, if it encounters a water molecule, is going to act as a base. And in acting as a base, it's going to take a proton away from water, generating acetic acid, the conjugate acid of this base. And then it leaves behind hydroxide. And again, in leaving behind hydroxide, this makes the solution basic. So that's our prediction. But now we're going to quantitatively determine just how basic it is by calculating the pH. So this is actually the first step in this equilibrium problem, writing the equation for what goes on. The next thing that we need to do is write the Kb. Now we write Kb because that's what the chemistry is that we're doing. We have base chemistry. So Kb is going to be equal to OH minus times HAC over AC minus. And we know that the AC initial concentration is equal to 0.25 molar. Equation, equilibrium constant, concentrations that we need in the right units. So we make our ice table. 0.25, water's not part of this. We're assuming negligible contributions from any other species initially. So some of our acetate ions grab a proton from water and generate the same amount of conjugate acid, the acetic acid, and hydroxide. So at equilibrium, we've got 0.25 minus x, and x. So Kb is equal to x times x over 0.25 minus x. Now here is where this problem becomes a little bit more complicated. If you set this expression equal to this value, you will get the wrong answer. And the reason is this is the Ka of acetic acid. We need Kb. So one important equation that we need to utilize to finish what has kind of been a cookie cutter standard equilibrium problem is the fact that we are given Ka. So we are given Ka and we need to get to Kb, and we need to know how to do that. So here's the last important equation here to think about. Kw is equal to Ka times Kb. And why this is important is we look at information that's given to us, right? Appendix C has a lot of Ka values. We've got 3 pages of Ka values. And then we only have a couple of pages of Kb values. But that's okay, because if you're given the Ka value, you can figure out the Kb value by using Kw. Okay, so in this case, we want to find Kb, so Kb is equal to Kw over Ka. Kw is 1 times 10 to the minus 14th The Ka that was given is 1.8 times 10 to the minus fifth. And so we can get Kb then equal to 5.6 times 10 to the minus 10th. So that's the only way this problem became like a tiny bit more complicated, is we weren't given the equilibrium constant for the reaction as written. Okay? But we can interconvert that by using Kw and the Ka that was given. But it's really important that you note that you have to use the Ka. If you want to get a Kb from a Ka value, they have to be these two related species. It's not like every single Ka value here is related to every other Kb value through Kw. Okay? If you want the Kb, if you have the Ka for the conjugate acid, you can use this equation. Okay, so hopefully that made sense there. So now we have the species that we need to continue what has been a typical equilibrium problem. 5.6 times 10 to the minus 10th. We're going to assume x is small, so x squared over 0.25 is going to be what that simplifies to. So then x is going to be equal to 1.2 times 10 to the minus fifth. Keep in mind, x equals hydroxide concentration. So if you just go ahead and take the negative log of this, you're not going to get the right answer. Remember, we did that on a previous sample problem where we just took the negative log of that and we got a very small value when we were predicting it was supposed to be a basic solution. So we went through and we took the negative log of that value and then took 14 minus that value, which was the POH value, to give us pH. I'm going to go around the corner in a different way here, and I'm going to say that to get H3O plus concentration, that's going to be equal to Kw over my hydroxide concentration. Again, Kw being 1 times 10 to the minus 14th. Our hydroxide concentration is what we just figured out. So that means my H3O plus is 8.3 times 10 to the minus 10th. Negative log of that is going to give me pH. So pH equals 9.08. Again, if we had taken the negative log of this, we would have gotten, let's see, 4.92. That's an acidic pH. We already predicted that our solution should be basic. Okay, so you need to make sure that you go through and kind of do a pre-check for what you think that's going to be. And I didn't, speaking of checks, I didn't check my assumptions, so I'm just going to grab my calculator here to check that. Our x is 1.2 times 10 to the minus fifth, right? And our initial concentration was 0.25. Multiply that by 100, and we certainly get something that's less than 5%. It's actually 4.8 times 10 to the minus third percent. So totally reasonable. And again, we can see that's because we have a very small equilibrium constant. Very little of this slides over here. But enough that we take and make the solution not neutral, but pH 9.